Welcome to qnawire.
Hi there. So for this problem, we have an horizontal plate that is experiencing an uniform irradiation on the both upper and lower surfaces. The ambient Earth's temperature surrounding the plate is given. Let's call this the temperature infinity is equal to 290 Kelvin with a convection heat transfer coefficient that is also given. Let's call that H, and that is equal to 30 watts per meter square per Kelvin. Both upper and lower surfaces of the plate have a radiosity that is also given. That radiosity that we're going to call Ju or JL, which is up or lower, is equal to 4,000 watts per meter square. And the plate temperature is maintained uniformly at a temperature, we're going to call this the temperature of the surface, Ts, that is equal to 390 Kelvin. If the plate is not opaque and has an absorptivity that is also known, and that absorptivity is equal, we're going to call that alpha, and that is equal to 0.527. We need to determine the irradiation and emissivity of the plate. So first, let me just draw this situation that we have in here for this problem. So we have an horizontal plate, something like this, and we have some radiosity. The radiosity is out of this plate. This is Ju and JL. We also are going to have some heat transfer to the ambient. And also we consider the irradiation that is into the plate. So with that said, by energy balance, let me just move this a little bit to the left. So by energy, we will have that this is 2 times the irradiation that we call J. In this case is total value, because we have for up and the lower sides of this plate, and then this is equal to 2 times the radiosity, and this plus 2 times the heat for convection. So with that said, for an area, a cross-sectional area that we consider of 1 meter squared, so you can see, in here, this A corresponds to the area. So we're going to consider 1 meter square of area. So with that said, the previous expression just simply becomes, we can cancel the 2's, and then we will have that this is the irradiation is equal to the radiosity plus the heat of convection. Now, first we're gonna obtain the rate of the heat of convection, and that is defined as the value given for the convection heat transfer that we call H times the difference between the temperature of the surface and the temperature of the surroundings. So that will be 30 watts per meter square per Kelvin. This times the difference between the temperature at the surface, that is 390, minus the temperature of the surroundings, that is 290, both in Kelvin. So from this we obtain a value of 3000 watts per meter square. Now to calculate the um, irradiation, we just simply substitute in the previous expression. Remember that we are given the radiosity, that is 4000 watts per meter square. So this plus 300 that we obtain, the 3000, sorry, the 3000 that we obtain for the rate of heat, the convention of heat. And then from this we obtain a value of 7000 watts per meter square. So that's the solution for the irradiation. Now we need to pass to obtain the emissivity of this plate. So for the emissivity, we know that the emissivity is going to be given by a quantity that we're going to call E divided by a thermal constant sigma times the temperature of the surface to the 4. Now this quantity E is defined as the radiosity minus alpha, which is the value given for the absorptivity, and this is 1 minus alpha. Here is 1 minus alpha, and this times the value that we obtain for the irradiation, and this divided by just simply in here this. So now we just need to simply substitute the values. So we will have 4000 minus 1 minus alpha. The value of alpha is given, that is 0.527, and this times the irradiation that we obtained from this, which is 7000, and this divided by the constant sigma. It has a value of 5.67 times 10 to the minus 8. This should be in units of watts per meter square times Kelvin to the 4. And this times the temperature of the surface that we are given, 390 Kelvin, and that to the 4. So from this, we obtain an emissivity of 0.5253. So that's a solution for this problem. Thank you.